Making mathematical online resources fair, at the example of small phylogenetic trees, by Bacher, Garrote-Lo, Görgen, and Neubert. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading this article which was published in 2026 in the notices of the AMS. In the past 2 decades, digital technology has transformed mathematical research, creating a vast ecosystem of preprint servers, collaborative platforms for writing text and code, and specialized online libraries. Many of today's valuable digital resources were born in the early 2000s, built with technologies and standards that are now dated. This creates a significant challenge. How do we preserve these resources, ensure their long-term value, and make them fully usable for a new generation of researchers? Digital preservation today is guided by the FAIR principle, which advocates for findability, accessibility, interoperability, and reusability of digital research results across the sciences. These principles do not insist on the use of the newest and shiniest web tool for presentation, replacing old standards by ever newer ones. Much more sensibly, they guide our decisions on selecting methodologies that preserve the long-term value and usability of digitized results. This paper presents a generalizable approach detailing how to preserve older digital libraries for the future. Rather than introducing new mathematical results, it serves as a methodological report and case study drawing on expertise from academic research data managers and mathematicians. We use the small phylogenetic trees library as a prototypical, valuable mathematical resource, offering practical guidance for others seeking to revitalize and sustain similar projects. The mathematical library Small Phylogenetic Trees, first compiled in the early 2000s, otherwise known as the Dark Ages, is a significant digital resource in the field of algebraic phylogenetics. It catalogs tables of algebraic invariants of evolutionary models on phylogenetic trees up to 5 species. These invariants provide insight into the algebra geometric structure of these statistical models and may be used for phylogenetic inference. We give a brief introduction to their mathematical description in section 2.1. Small phylogenetic trees supplements the invariants with code, raw computational output files, and a documentation of the terminology used. 20 years later, it remains an actively used online resource for researchers in algebraic phylogenetics, but no longer fully meets contemporary digital standards. The origins of many mathematical digital resources, including small phylogenetic trees, lie in the technological environment of the early 2000s, when the digital landscape for mathematics was expanding rapidly with the public internet. The now famous Online Encyclopedia of Integer Sequences, or OEIS, available at oeis.org, had been online for about a decade after 2 decades as a book, while the equally famous L Functions and Modular Forms database, LMFDB, also based on earlier books, was still just a vague idea. The archive preprint server was yet to reach 500,000 articles, and prominent mathematicians such as Gowers and Tao had just started their blogs. The version control system Git had only been recently launched. In this environment, the goal of small phylogenetic trees to make available in a unified digital format the known computational results in algebraic phylogenetics was modern and visionary. Today, the situation has changed significantly. Digital Object Identifiers, or DOIs, introduced at the turn of the century, have become standard for citing publications, in many aspects taking over the role of ISBNs for identifying books. Git repository services like GitHub and institutional GitLab are now indispensable for collaborative coding. Web technologies now allow dynamic presentation of a lot of data on a single page. Powerful open-source software for symbolic computation rivals commercial alternatives. Knowledge graphs can link mathematical results directly to their formalizations and related papers, and mathematical notation may be displayed and annotated using, for example, LaTeX and MathML. By today's standards, the Small Phylogenetic Trees library appears dated. Is it FAIR? Are its results verifiable? We will analyze these questions. Our approach is threefold. 1. We launch a new straightforward presentation of the original website content built as a collaborative project. We select a single software environment capable of computationally verifying every result on the website, and we use it to develop a comprehensive package for algebraic phylogenetics. 3. We compile this text as the third component, tracing our methodology, decision-making processes, and implementation details. This crucial aspect of the project was not documented in the original book chapter on small phylogenetic trees, but we consider it vital to enable the community to follow by example. Our primary objectives are, firstly, to enhance the library's adherence to the FAIR principles, and secondly, to ensure the long-term reproducibility of its mathematical results. Thus, in Section 3.2, we document the details of our strategic approach, and in Section 3.3, we describe the outcomes achieved. Finally, in Section 4, we derived guidelines to support the sustainable modernization of other similar digital mathematical resources. Background. Although theoretical proofs will always be at the core of mathematics, modern research increasingly relies on computers to perform complex calculations and to analyze large sets of information. Online mathematical libraries such as the OEIS, LMFDB, and small phylogenetic trees have become the modern successors to lookup tables and classifications in book form. They're easier to update than their traditionally printed counterparts. They consolidate information in one place rather than spread out over a series of articles. And they serve as active tools where researchers can test conjectures against a wide range of cases, compute examples, and access hard-to-find results, thus saving significant time, effort, and energy. Algebraic phylogenetic models. Small phylogenetic trees self-describes as mainly a repository of algebraic information of different evolutionary models based on trees with a small number of leaves. Specifically, it focuses on nucleotide substitution models describing the evolution of DNA sequences composed of the nucleotides A, C, G, and T on phylogenetic trees of 5 or fewer species, or taxa. Figure 1b shows a screenshot of such trees. Let's take a look. Figure 1b, a screenshot of some such trees. The caption says, Figure 1, screenshots of small phylogenetic trees, January 2025. On the left, the landing page. In the middle, an overview of all trees considered. And on the right, data on the 3-leaf phylogenetic tree with Jukes Cantor model. These models assume that DNA sequences evolve according to a Markov process on a given phylogenetic tree T. A random variable representing a nucleotide is associated with each node of the tree, and the process is governed by two key parameter sets. 1. A probability distribution at the root of T, and 2. A 4x4 transition matrix associated with each edge. This setup defines a polynomial map phi sub T that sends the collection of free parameters, namely the root distribution and the transition matrices, to the joint probability distribution P equals PAA dot dot A, PAA dot dot C, dot dot PTT dot dot T, of observing specific nucleotides at the leaves of T. These models can be viewed as algebraic statistical models, since the set of all possible distributions P in image of phi sub T that can arise from a phylogenetic tree lies within an algebraic variety Vt, the Zariski closure of the image of phi sub T. This variety is defined by a set of polynomials that vanish for any valid distribution generated by the model. They belong to the ideal of V sub T and are known as phylogenetic invariants. Kind of funny how the authors shoehorn algebraic geometry into this paper where it's completely inappropriate. Obviously, because right now algebraic geometry is totally eating the whole world of mathematics research. The authors continue. While the theoretical properties of phylogenetic tree models have been extensively studied, computing phylogenetic as well as algebraic invariants such as the dimension or degree of Vt or its singular locus is a significant challenge. These computations often rely on having a Grobner basis for the ideal of V sub T at hand, notoriously computationally intensive even for trees with relatively few taxa. This computational bottleneck is precisely the problem that the catalog of small phylogenetic trees addresses. The user does not have to perform extensive computations or browse papers, but may simply look up algebraic invariants already computed and made available by trustworthy peers. The library focuses on a particular class of nucleotide substitution models known as group-based models, such as the Cavender-Ferris-Neyman, Jukes-Cantor, and Kimura models. These allow for a Fourier transformation to simplify the parameterization of Vt. After this linear change of coordinates, the models correspond to toric varieties, making their phylogenetic invariance significantly easier to describe and compute. The website catalogs a range of these algebraic invariants. For each model and tree, it contains data like the dimension, d, and degree, small d, of Vt, and its singular locus, sd, and s small d, respectively, or the dimension of the linear space containing the probability distributions, np. Alongside the algebraic invariance, the website lists the parameterization Vt in both standard and Fourier coordinates, and is defining phylogenetic invariance. For instance, we see that the maximum likelihood degree, a measure of parameter estimation complexity for a 3-leaf tree under the Jukes counter model, is a manageable 23, while the corresponding value for the 5-star tree remains unknown. Without diving into computational details, a researcher can learn from small phylogenetic trees that the corresponding toric variety for the 5-star tree has dimension 6 and degree 115, lies in a 27-dimensional linear space, and is defined by 175 polynomial equations of degree 4 and 5. Maybe I spoke too soon when I said it was inappropriate to mention algebraic geometry here. Is this really related to algebraic geometry? I might have to read up on it more on the side. Anyway, Section 2.2. FAIR, reproducible and open mathematics. The FAIR principles are well established and widely accepted for assessing the sustainability of digital research artifacts such as papers, code, data, or software. They comprise 15 criteria that help both human and machines determine whether a resource and its description is findable online and persistently so, who is allowed to access the resource, and technically how the resource and its description can be accessed, whether the resource is interoperable with its environment, whether as well as under which licensing it may be reused. These sorts of things, these sorts of checklists are sort of noble, but often tend to be latched onto by bureaucrats and so on, and they don't provide nearly as much value as you would think. But they tend to be ways of filling grant proposals with buzzwords, and that's how they're often used, really. Actual workers in the field rarely would even be aware of these concepts, much less give a hoot about them. Anyway, the authors continue. FAIR-ness shall not be confused with reproducibility. While the former may be read as available and usable, we read the latter as verifiable. Thus, FAIR mathematics is not necessarily good or understandable mathematics, but a FAIR research output is a necessary first step toward assessing its reproducibility. Likewise, the accessibility A in FAIR should not be confused with open access. Although there is a strong open access culture in mathematics, with preprints freely available under Creative Commons BY licensing on archive.org, FAIR accessibility is fulfilled if data and metadata are machine readable, for instance via an API. The data itself does not need to be open as long as its metadata is available. Side remark here, this focus on APIs, which has been a thing for many decades now, I speculate that AI will make this less of an issue, because as AI gets better and better, people will just use AIs to parse stuff in human readable format or in ad hoc machine readable format without some published schema necessarily. So just like the Web3 OWL ontology stuff, I think that this stuff is aimed for the scrap heaps of history. But let's continue. Whilst the FAIR principles are the key guiding principles for data management across the sciences, they are currently not widely known or consciously applied within the mathematics community. There are, of course, flagship projects of mathematical databases like the OEIS and LMFDB, whose online presentation lives up to the same high standards the community applies to their theoretical findings. But we were unable to find general advice on how to make small phylogenetic trees as FAIR or reproducible as these big players. The National Research Data Initiative, NFDI.de, in Germany is likely the largest national effort to promote FAIR research data, with its mathematics-specific consortium, MARDI, providing insight on how to apply the FAIR principles specifically to mathematical artifacts. Okay, insight into this from someone who did a postdoc in Europe working on Web3 ontology stuff, which is closely related to this. The reason why you see Europe as the big center for this sort of thing is exactly what I was just saying, that this stuff is used to sprinkle buzzwords into grant proposals, and Europe, the EU, is particularly susceptible to this kind of buzzword-driven grant proposal process. It's quite crazy. You just throw enough buzzwords in the proposal and the EU will throw money at you. The authors continue. The NFDI is part of international initiatives such as the European Open Science Cloud and the Research Data Alliance. Current guidelines from general scientific funding bodies primarily focus on the FAIR-ness of typical research data types like datasets, publications, and software, offering little to no guidance specifically tailored to online mathematical libraries like small phylogenetic trees. The Marty white paper and the analysis by Marty authors are, as far as we are aware, the only current resources providing some guidance and initial assessment of the FAIR-ness of some mathematical resources, but no suggestions on how to FAIR online mathematical libraries either. This paper aims to close that gap. Yeah, again, I can offer insight into this from personal experience. Everything in these spaces, I'm familiar with the Web3 OWL ontology space from my postdoc work, but this space I imagine is totally similar, this FAIR space. Everything in the space is put online by some academic in a temporary sort of location and promptly dies. Any software which is related to this will almost certainly be written in Java, and you'll go to download the dependencies and you'll find they're all dead links hosted on academic websites where the academics moved away years ago, stuff like that. Ironically, the very thing that this FAIR is claiming to fight against. The authors continue. Section 3, FAIR-ifying small trees. Analyzing the website. Careful thought and effort has gone into small phylogenetic trees. Before assessing its current state of FAIR-ness and reproducibility, we provide an overview of the library's design and content. The website is structured like a traditional catalog reflecting early 2000s web practice. Its landing page sports a table of contents, mathematical background, notation and tree labeling conventions, errata of the print version, and a comprehensive table of small trees considered. It links to news items dated from 2005 up to 2007, suggesting active maintenance in that period. The table of trees then enables a user to dive deeper, navigating through a subpage with all nucleotide substitution models considered for a given tree to a subpage with algebraic invariance and code for each particular choice of tree and model. While the library's structure is timeless in its logic, its full potential is hindered by this nested design, in these authors' opinion. Together with the use of unintuitive subpage identifiers such as numbers rather than descriptive names, navigation is difficult for new users and broken author links evoke an outdated first impression. Now what can we say about these data? Findability. Small phylogenetic trees is hosted by the main maintainer's academic institution and can be found through a general search engine, even if the direct link in the original paper is broken due to a change in affiliation and the database title does not match precisely. Researchers may use both the hardly memorable URL to refer to small phylogenetic trees or cite the corresponding book chapter. Par for the course for academia. Accessibility. The website uses the HTTP standard protocol. There's no mechanism in place to download data or code other than manually navigating through subpages using copy and paste. Outdated file formats such as GIF do not allow users to access the input of computations such as the tree in an automatized way. Interoperability. The code is supplied in two programming languages which are standard in the field, commercial Maple and open source Singular, enabling the user to make a choice compatible with their own preference and budget. Interoperability is hindered by the absence of input-output specifications, detailed software requirements, and versioning, and by poor documentation. How variable names in the code relate to the underlying theoretical concepts is in places hard to trace. This is... If you can't teach. If you can't even teach, get on a committee writing standards documents. That's what this is. Nobody in the industry cares about any of this at all. Reusability. Each subpage of the resource includes a timestamp, typically 2006, and an author, typically key maintainer Luis David Garcia Puente, providing some versioning and accountability. There is no license attached to the data or code, making it legally not usable. However, all contributing authors are linked to their personal homepages and may be contacted for reuse. Not that it's legally unusable, that is an incorrect statement by these authors. Rather, many corporate bodies, legal departments would not want you to use them. Now, if it were a life or death situation, you could get those lawyers to make an exception. Certainly, it's not that it's legally not usable, it's that the lack of a license makes quasi-corporate bodies hesitant to use it. That said, it would be better to put a license on there. Just slap an MIT license on it. It's literally just adding one file to the web page and one link on the front page. Anyway, we may assume that the lack of licensing is due to a typical pitfall for newcomers in research data management, namely assuming no license would imply free usage. This is not the case, but understandable given mathematics' culture of openly sharing results. The interoperability in FAIR is also interlinked with how reproducible the data turn out to be. Reproducibility. Standard algebraic phylogenetics definitions, illustrations, and naming conventions help a user familiar with the field to trace a mathematical argument. However, important data such as the polynomial parameterization Vt of Vt and its phylogenetic invariance are hard-coded. That is, the provenance of key mathematical results is undocumented. This absence of methodological and computational transparency hinders direct verification. Especially for newcomers, considerable effort is needed to make results on small phylogenetic trees interoperable with and verifiable on their own systems. So at present, small phylogenetic trees fulfills some of the FAIR principles and is partly reproducible with sufficient domain knowledge and coding skills. But does this mean it is not trustworthy? No. The resource's credibility is established by its attention to authorship, the standing of authors in the community, underlying papers which have passed peer review, and a broad and educated user base in the community. What we can do to improve the current state of the library is to make every aspect, from display and data retrieval to reuse and reproducibility, significantly more straightforward. Making a plan. We decide to address concerns raised in our analysis above carefully and separately by splitting the computation of algebraic invariants from their display, by supplementing a new website with a new software package. This enables us to both modernize the presentation and independently to provide proof in a single software package that stores all necessary information, definitions, functions, inputs, and outputs in one place. The software we decide on is the computer algebra system Oscar based on Julia. It can save mathematical objects together with their context, e.g. for phylogenetic invariant, a specification of the ring in which the polynomials live. The software is further able to call both symbolic and numerical methods, so there's no need to switch systems when trying out different approaches to compute algebraic invariants. Usability, both technically as well as visually, is our foremost concern, and our website and software approach allows us to differentiate between levels of user need and skill. The website itself shall be easy to navigate for the interested pure mathematician or newcomer with no coding skills. For those in need of code and detail, each result displayed shall be linked back to a paragraph in the software package's documentation, as well as to the respective lines of underlying code in a serialization file, ideally supplemented also with citations of theory. All technical detail is thus made available for researchers to embed computational results directly into their own work. This interconnectedness of data, invariants, formulae, formalizations, code, and publications enables both human users and machines to grasp mathematical results and generate knowledge. For efficient teamwork, to clarify priorities, and to make sure we address both FAIR-ness and reproducibility, we draft 3 plans. One data layout plan and one research data management plan, both for the software and the website. The first, displayed in Figure 2, illustrates what data and data relations we find in the small phylogenetic trees library and how these build on each other when reproducing results. The latter plans in Figure 3 build on this. They formulate a data handling strategy for the software and the website, clarifying how to treat all occurring files and data formats during and after the project, ensuring they are handled FAIR. We start with the data layout plan in Figure 2 to better understand the structure of small phylogenetic trees. Now, this Figure 2 here is the sort of thing which you'll see used by middle managers and so on and so forth. No mathematician would ever draw a figure like this. It's pure bureaucracy, pure slop, pure corporate slop. The authors continue. For each phylogenetic tree and each phylogenetic model listed at the very top of the chart, we can compute a number of algebraic invariants abbreviated and listed at the very bottom. The workflow from input to output requires a human to infer modeling assumptions from a picture and write those into some computer algebra system used to compute phylogenetic invariants, as well as the rest of the algebraic invariants. The overview of all the steps involved in this process enables us to identify which ones need to be formalized in a comprehensive software package. We mark these missing in the plan. The chart serves as a basis for making the following decisions for improvements. To display input, model, and tree, and output algebraic invariants on the new website in one single big table. To display in-between computations such as phi sub t or the phylogenetic invariants on an individual subpage for each tree/model combination linked to directly from within the respective cell of the main table. For the software package to decide and implement the input structure, write functions for every computation of relevance, store the output in an interoperable format. Having, thanks to the data layout plan, understood which data need to be reproducible, we then address our goal of developing future-compatible FAIR online mathematics. This is based on two pillars. First, we make machine-readable every file and every piece of mathematics we handle to be actionable for semantic web technologies. See? Semantic web. That's the buzzword which clues you in that this is a bunch of grant eliciting bait on their fishhook. First, we make machine-readable every file and every piece of mathematics we handle to be actionable for semantic web technologies and thus ready for coming research data infrastructure tailored to mathematics. Okay, when they say machine-readable, they are demonstrating that they live in the 1990s and have never even heard of large language models. The authors continue. And second, we make human-readable every such piece of data via extensive documentation, thus preserving its value in case technology ceases to exist. And no human will ever read that documentation because the things being documented are obvious to the plain eye to anyone who's actually using the data. Now, to achieve that goal, we plan which data types we generate and how they are treated along their life cycle. For instance, we prefer open source data types like .tex for the report and .mrdi for computational results, and we prefer data files which are understandable and readable by humans like .yaml for the data displayed on the website. The .yaml files are, at least regarding their mathematical content, duplicates of the .mrdi files. We need both because the latter are not yet printable. Both are reproducibly generated automatically from our code. Moreover, we choose Git technology for versioning and collaborative coding, in particular GitHub for active code development and an academic GitLab instance for long-term website hosting. The research data management plans documenting these decisions are displayed in Figure 3, which I will not give the dignity of reading. They are set up after a phase of exploration and before we take up any of the actual work, and they follow an established structure, employed e.g. by the data management community and funding bodies. Funding bodies, that's what is most important here. Money, money, money. To address management as well as practical responsibilities, rather than being a mere bureaucratic addition to the core mathematical work. Actually, that is exactly what it is a mere bureaucratic addition to the core mathematical work. We claim they make it easy for us to focus because all possible distractions are clarified in advance, in particular the order in which to perform tasks, whom to attribute which role to, how to keep track of progress, and most importantly, how to handle and preserve results long term. How did this get accepted to the notices of the AMS? Good heavens. Section 3.3, Analyzing Our Achievements. At the time of writing, an experimental version of our software is available, and so is version 0.1 of algebraic-phylogenetics.org. In Figure 4, we present two screenshots of our new website. The landing page consists of a large table indexed by tree and nucleotide substitution models containing the algebraic invariants. This allows researchers in phylogenetics to quickly access knowledge. At the top left of the page, there are two links directing users to subpages on notation and terms of use, respectively. Two additional links in the top right lead to small phylogenetic trees and to algebraic phylogenetics. From the main table, users can directly navigate to the subpage of interest to find additional algebraic information about specific trees and models, and to integrate relevant computations and formulae into their own work. We made improvements in the handling of mathematical data as well as in their metadata description. These are in particular of the following kind. Findability. The new domain and name, the Algebraic Phylogenetics database at algebraic-phylogenetics.org, refer directly to the mathematical field, and we state the respective MSC identifiers for findability. The homepage has its own citation guideline, which is distinct from text reports like this one and from the software citation for added precision and appropriate credit. For long-term preservation and citability, each past and current version of the website is stored at zenodo.org as a snapshot of our GitHub repository. These means increase findability both for the human user and for automated online search engines. Additionally, we link all authors to their ORCIDs and personal web pages, and we set up a maintainer's email address. This enables users to directly and correctly identify lasting contact points. Relevant publications in algebraic phylogenetics are linked via DOIs for persistence. Moreover, algebraic phylogenetics benefits from Oscar's SWHID for long-term traceability. Accessibility. Metadata for each combination of phylogenetic tree and model are gathered in files which are both machine and human readable for immediate accessibility and long-term understandability. In particular, this information is stored in YAML files which are hosted on GitHub and accessible via GitHub's REST API. REST! That's another of these buzzwords. In actual software development, generally nobody gives a flying bean about restfulness, but it has become this buzzword which useless bureaucratic management types love to throw around, and what little use it had is completely obsoleted by agentic AI. The authors continue. Formulae inside these files are typeset in LaTeX as is custom in mathematics, machine-readably rendered on the website using mathjacks, and trees coded in TIX and displayed using TIXJAX. Each mathematical object is additionally available in open-source.mrdi files based on JSON, which can be loaded in Julia, thus containing valuable mathematical metadata, again in machine-readable and human-readable format. License statements on the GitHub projects underlying the website as well as the software give access to any interested user. Interoperability. Regarding interoperability for the human, we reiterate standard notation, document our computational workflow, and provide usage examples for the software package to facilitate integration into external projects. Maximum machine interoperability is achieved by choosing the open-source computer algebra system OSCAR, which integrates ANTIC, GAP, polymig, and singular. All of these widely used in computer algebra. Here, the Julia basis has the potential to facilitate the combination of both numeric and algebraic calculations in algebraic phylogenetics. The .mrdi format can provide both an interface between website and software as well as serialization, allowing to meaningfully save and load computations, much preferably to copying and pasting LaTeX without context. Reusability. Extensive documentation both on the website itself and externally in OSCAR make it easy for the newcomer to dive into details. Permissive open licenses are chosen and clearly stated for displayed results, computer algebra software, and the website build. Every result is further linked to a copyable LaTeX display of formulae and to GitHub or OSCAR code, performing relevant computations, making results traceable, and boosting reproducibility and trustworthiness as is good scientific practice. In this way, we have created an online resource that is as FAIR as our technical expertise, time constraints, and currently existing mathematics research data infrastructure have enabled us to build. Regarding the reproducibility of results in the library, we have made the following improvements. Reproducibility. Coding in open-source software enables the users to check every function and data type we defined. The software algebraic phylogenetics captures all the computations in one place as opposed to missing intermediate steps or results spread out over many different files. We provide extensive code documentation in OSCAR's style guide using the Julia documentation feature, and we link all data displayed back to the code. Data files are easily identifiable thanks to the new file naming conventions. Any outsider can now simply redo computations and verify the data comparing input to output. Serialization provides extra reproducibility by seamlessly fitting into existing OSCAR environments. Versioning of our software enables practitioners to check compatibility. Our software passes the newly formulated guidelines for writing and reviewing software in computer algebra. Both Julia and OSCAR are existing academic projects with big communities. This enables us to draw on developers' expertise, acquire new users, greatly improving chances of long-term maintenance as opposed to a standalone project, and crucially increase the chance that our work will continue to be FAIR and reproducible for the future. Maybe if you extend it to beyond 5 species, but assuming it remains at 5 species, then this is an example of a project which I assume is finished. Not all software needs to constantly be updated. This is something which people in software development circles kind of lose the plot on. Thus, You have Microsoft adding AI to Notepad, which of course lots of people complain bitterly about. It's just silly. The database only covers up to 5 species. It's a small finite amount. The project's done. It doesn't need a team maintaining it continual in perpetuity. Oh, but that's not how you get grant money, of course. The authors continue. We anticipate that the database will continue to grow with current interest in the phylogenetics community. In future versions, we plan to incorporate algebraic data related to phylogenetic networks as well as additional nucleotide substitution models, such as algebraic time-reversible models. This opens the door to external contributions, both through direct involvement in development and by sharing emerging interests, improvements, or updates that should be reflected in the database and accompanying software. So maybe I spoke too soon. Maybe there is stuff that they're planning to add, which isn't already there. In that case, they should just create a new project. Create a whole new project from whole cloth. Rather than this stuff. But again, they would then not get grants from granting agencies who are blindly funding these FAIR projects. Section 4, Learnings and Guidelines. Being a rather large team with heterogeneous expertise in computer algebra and managing 3 projects simultaneously, our learning curve was quite steep. The primary tool for collaborative and version-controlled coding is Git, so we needed to become familiar with sensible workflows. Due to initial indecision about whether or not to join the OSCAR system, we confusingly established different repositories with the same scope existing in parallel. If we'd devised a plan ahead of coding, we would have been able to make informed decisions on what platform to use in which manner exactly, e.g. for website hosting. It came as a great opportunity that we were able to join the algebraic statistics module in OSCAR. As a consequence, we had a say in overarching design decisions from the OSCAR codebase to the serialization system using the .mrdi file format. Additionally, we benefited from the existing technical and support structures. However, with all projects in active development, we had to adapt our internal progress to external progress. We initially did not rely on a dedicated project management tool as we should have, but started multiple communication channels, effectively hindering efficient collaboration. Typical hurdles such as fixed-term contracts and incompatible time zones were the straw that broke the camel's back, leading to a project runtime of nearly 1.5 years rather than the optimistically anticipated couple of months. Well, in software, you always multiply your estimated time by at least a factor of 6, if not 10. In particular, MN continued to work for free for months after his student assistance officially ended, preparing himself exceptionally well for a career in academia. Sick. Burn. How to. It is easy to criticize other projects, difficult to do better, but fellow mathematicians appreciate the effort. We thus wish for the development of algebraic phylogenetics.org to serve as a prototype for similar projects, leading to increasingly sustainable, usable, and trustworthy online mathematics. We recommend the following. Plot. Spoiler. All of this is completely pointless in the age of agentic AI. Anyway, the authors continue. Draw in all expertise available. Discussions with data stewards, information specialists, computer scientists, computer algebraists, mathematicians who are in our community or own similar projects in other fields have helped us shape an idea of what's possible and what's needed to make algebraic phylogenetics both FAIR and reproducible. Consult research data management experts. In particular, we based our work on advice from research data initiatives like FAIR.org and MARDI, as well as implementation discussions following the original publication of FAIR principles. Focus on usability. All great work is for naught if it is not used. So we first compared notes with researchers who use small phylogenetic trees actively, identifying pros and cons of the setup. We wondered who does not use the library but would use it if we could make the content more understandable. As a result, we put the lookup table centrally on the new website's landing page to enable everyone to get a grasp of the content, with the details for experts found further down the website tree. Investigate community needs. The data layout plan and reviewing active research on algebraic phylogenetics enabled us to trace the workflow of researchers using small phylogenetic trees. In order to help with the main hurdle, integrating results into their daily work, we put a priority on linking computational content and theory more directly. Identify gaps. The key points which make small phylogenetic trees appear outdated are the early 2000s timestamps and partially broken list of maintainers. We want the algebraic phylogenetics database to be up to date with current research and visibly so we established contribution guidelines, versioning, and merged old data with new. This makes me think of a phenomenon that you have where people will put superfluous commits to a repository on GitHub just so that people will see that the most recent commit is recent. It's silly. If a project's finished and done, then it's finished and done. Let it rest. But people are misusing the date of most recent commit as a metric for judging the trustworthiness of the project or something. It's inappropriate. Anyway, to stop each researcher writing their own code to fill gaps between presented results and question of interest, we set up the collaborative software project. Include documentation. By making all code readable for humans, providing versioning of all digital resources, having permanent digital identifiers, and interlinking as many objects as possible, models, papers, code, etc., we soften the impact of a number of dangers, that the software system we use may break, that the programming languages we use may die, that modern web technology evolves faster than we do. In short, that our currently very modern presentation will become one day as outdated as databases printed in books are today. Well, that's kind of a non-issue with agentic AI. By the time currently used languages die, say Python or Oscar or whatever, certainly you'll just be able to point in agentic AI at the data at the repository and tell it to upgrade it to whatever new language, and that'll be an easy task, especially if you include tests, which, by the way, they mention nothing about tests here, at least so far, which would be far more valuable as far as these purposes go. Software tests. Anyway, make it sustainable, they continue. The job interview question. Where will our database be 10 years from now? The math will still be true. To keep it FAIR and reproducible, we make it human as well as machine readable. We found an academic institution to host the website for the foreseeable future, and we established a community of maintainers with shared contact info, assigning one person the main responsibility. By choosing well-known Git technology for external contributions, we enable the algebraic phylogenetics community to actively sustain our project. Link it to larger infrastructure. The FAIR principles require metadata to be persistent even if the data themselves are no longer available. To achieve this, we plan to put relevant metadata of the classification on Wikidata to supplement our Zenodo snapshots. This way, both data and metadata can be automatically harvested by online search engines and integrated into broader knowledge graphs for mathematics and neighboring disciplines. Knowledge graphs. Again, this is this semantic web nonsense, which is just the apple from the Garden of Eden when it comes to getting those European bureaucrats to fork over taxpayer money for wasteful work. Anyway, with the MARDI portal growing and interlinking formalized mathematics with paper theorems, the time for this type of integration is, the authors say now, but the true answer is yesterday, before we had AI, and now the work's no longer needed. Acknowledgement. This project is a community effort. We are hugely indebted to the authors of the original small phylogenetic trees for enabling us to continue their legacy. Marta Casaneas, Sorkin Hoshton, Luis David Garcia Puente, Jacob Porter, Leor Proctor, Stacy Stokes, Bern Sternfels, and Seth Sullivan. In particular, we're very grateful to Luis David Garcia Puente, the principal maintainer, who provided us with valuable input in initial discussions, generous access to the original website files and data, and many thoughtful comments on this manuscript, and endured the pain we inflicted when criticizing his creation. The software supplementing the database algebraic-phylogenetics.jl and algebraic-statistics.jl would not have been possible without the ongoing practical support and sharing of expertise of the Oscar group, especially Antoni Dea Vecchia, Lars Kastner, Michael Joswig, and Andrei Komenici. We also wish to thank Tobias Boasia and Ben Hollering for technical help and fruitful discussions about the implementation of mathematical concepts within our software project. The Max Planck Institute for Mathematics and the Sciences supported MGL and MN in the early stages of this project and continues to support TB. We are immensely grateful for their acquisition of the domain and for hosting the GitLab fork of the GitHub project underlying algebraic-phylogenetics.org. TB, CG, and MN were supported by the Mathematical Research Data Initiative, MARDI, funded by the Deutsche Forschungsgemeinschaft, project number blah blah blah. MARDI, Mathematische Forschung Data Initiative. MGL was partially funded by the Institute for Computational and Experimental Mathematics under an NSF grant. While in residence at the fall 2024 semester program on Theory, Methods, and Applications of Quantitative Phylogenomics. Peter Bellman's phenography.info served as a conceptual blueprint and inspiration for our project. We wish to thank him for making time to consult with us and for providing many helpful pointers before we embarked on this journey. Yeah, I like that the notices gives us some insight into this sort of thing, but I think the paper is far too long for what it says. You get the sense from hearing me read this that I'm not a fan of this bureaucratic guideline type stuff. I think this is contributing very little value, at least the FAIR stuff. It sounds like what they're doing is they're creating a new version of this small phylogenetic trees project because the small phylogenetic trees project is lacking certain data which they wanted to add, and that's fine, that's great, make your new version. The whole FAIR stuff, that's just a gigantic red herring which they used in order to get taxpayer money to fund the students doing this. So I guess they are providing some value in creating the new library, the replacement of the original small phylogenetic trees library. But this whole FAIR stuff is a bunch of smoke and mirrors to steal taxpayer money, basically. I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. I'll see you in the next video.